The purpose of this video is to provide some additional examples of Lenz's law. Since Lenz's law uses right-hand rule number 1, I want to review that again first. So in this example, we have a loop of wire, as shown, sitting above a current-bearing wire, and the current's increasing, but the fact that it's increasing isn't actually important right now. What we want to get right now is what is the direction of the magnetic field through the loop. So you can see there's a current with the current going to the left, and there's a loop of wire above it. So here's my loop of wire, and you have a current going to the left, going that way. So if you're trying to figure that out, you point your thumb in the direction of the current, and your fingers go through the loop in the direction of the magnetic field. So as you're looking at it, it would be into the page. Whenever I work on these for the camera, I'm always doing it backwards. So if you're trying to do it with your hands, it wouldn't look exactly like that. So I'm actually going to turn around this time in case this might help. And here's the loop of wire. And so now you're looking at it. We're both at the same point of view. So the current is going to the left. And what's the direction of the magnetic field from that current-bearing wire? I point my thumb in the direction of the current, and my fingers go through the loop into page through the loop. So the direction of the magnetic field through the loop is into the page or away from you. All right, so I hope that helps a bit to review right-hand rule number 1. We'll do it a few more times, but I hope that helps. So remember, the current is forming a magnetic field, and the magnetic field is in a circle around the wire. So I'll go back to this perspective again. The magnetic field from a current-bearing wire that's below the wire is going through the wire, away from you, above the wire. Below the wire would be coming back around and be back towards you, as shown in that example. Okay, let's try some of these problems. So we'll go through these. The 3 steps that I show on the right side are the 3 steps given in your book. I've removed the highlighting so that you hopefully can think through them on your own a little more easily. So determine whether the flux is increasing, decreasing, or unchanged. And it doesn't state it in that step, but you should also figure out the direction of the magnetic flux because you'll need that in the next step. So if the current is increasing, the magnetic flux through the loop is also increasing. So this current-bearing wire has a magnetic field. From right-hand rule number 1, we already figured out direction magnetic field is into the page. And if the current is increasing, the strength of the magnetic field is increasing, so the magnetic flux is increasing. There's more magnetic field going through that circle of wire that's just sitting there. So there's a change in flux, there will be an induced current, and the next 2 steps we figure out the direction. All right, so if the current's increasing, again, then the flux is increasing, and the direction, as we just figured out at the beginning, this is the very example we had for our review of right-hand rule number 1, the direction of the magnetic field is into the page. All right, step 2, you figure out the direction of the induced magnetic field. If there's a change in flux in the loop, then there'll be an induced current in that loop. The induced current has a magnetic field that opposes the change in flux. That's what we're working out. And the words here help us figure that out. So it says the magnetic field due to the induced current points in the opposite direction to the original field if the flux is increasing, in the same direction if it is decreasing. So we just figured out it's increasing. So the magnetic field due to the induced current points in the opposite direction. So it will be pointing outward. All right, my shorthand for that, which I'll give you now, is that the induced magnetic field opposes the change. So if the magnetic field going through the loop is increasing, to oppose that change, we need an induced current that has magnetic field in the opposite direction. That's this case, so it'll be out. In contrast, my shorthand, if the magnetic field going through the loop had been decreasing, then there'd be less magnetic field going through the loop. So to oppose that change, you need more magnetic field going through the loop. So it would be in the same direction. That's what's said here in words, but sometimes you can apply the words without really thinking. So if you think it through, we are creating a magnetic field that opposes the change in flux. So we have the magnetic field from the induced current, so a current induced in this coil, and it will point out back towards you. And so now we do right-hand rule number 1 to figure out the direction of a current in this coil that will give us a magnetic field that points out. we no longer care about the original direction of the magnetic field. Everything we figured out in step 1 about the current bearing wire and everything, we have the answers we need from that. So we drop that information. Our next step is to use the right-hand rule to get the direction of the current. So we want a magnetic field that points out, and again, I'll turn around so that things look the way they would if you were doing this. So to get a magnetic field to point out through the loop, I always grab from the bottom of the loop. So if I want a magnetic field that points out through the loop, there are my fingers coming around the coil, pointing out through the loop. My thumb points to the right at the bottom. That's going from 6 p.m. back to 3 p.m. That's counterclockwise. So we're done. We have our result. The induced current has to be counterclockwise, having followed all those steps. And there we are. All right, let's do another one. Again, we have a situation with a loop and a current-bearing wire. We want to determine whether the flux is increasing, decreasing, or unchanged. That's step 1. If the current is decreasing, then the magnetic flux is decreasing. You can go back and look at the equation for magnetic field from a current-bearing wire, and it's directly proportional to the current. So if the current drops, the magnetic field drops, and that means the amount of flux going through the loop will also drop. So we know it's decreasing. We also want to figure out the direction, so we'll do that again. We have our loop of wire. We have our current going to the right this time. So from a current-bearing wire, if the current's going to the right, I wrap my fingers sort of around my imaginary wire up here, and going through the loop below it, the direction of the magnetic field will be into the page. Above the current-bearing wire, it would be out of the page. Below the wire, the direction of the magnetic field is into the page. So it's decreasing, and the direction points inward. So step 2, the magnetic field due to the induced current points in the opposite direction to the original field if the flux is increasing, in the same direction if it is decreasing. And it's decreasing, so it'll be in the same direction. We already figured out that direction is inward. So we know the magnetic field due to the induced current has to point inward. Final step, use the first right-hand rule to determine the direction of the current. So all we have to do is look at our loop and figure out the direction of the current so that we get a magnetic field that points inward. And again, I'm going to turn around, and I always grab from below. So from below, if I grab so my fingers go in from below, then my thumb is pointing, say, from 6 o'clock to 9 o'clock. That is clockwise. I could grab from above. If I grab from above so my fingers go inward, now I'm going from noon to 3 o'clock. It's still clockwise. Or I could grab from the side. And as long as my fingers are going in through the loop, then now I'm going from 3 o'clock to 6 o'clock. It's still clockwise. Doesn't matter where I grab it. I just find it easiest to grab from below. So we have our result that the induced current is clockwise. All right, let's do another one. Determine whether the magnetic flux is increasing, decreasing, or unchanged. If the current is constant, then the magnetic field from that current-bearing wire is constant. It's there. There's a magnetic field going around that wire. We could figure out the direction of it if we want to, but it's not changing. If the current is constant and the strength of the magnetic field is constant, there's no change in flux through that loop. There's no induced current. So that's a quick one. No current. All right. Another one. Determine whether the magnetic flux is increasing, decreasing, or unchanged in this scenario. So again, we're trying to figure out the direction of the induced current in this coil, if any, and we go through our 3 steps as outlined in the book. If the current in the wire is increasing, then the magnetic field generated by that moving current is increasing. So we have an increasing magnetic flux. This step, I also like to get the direction. So if the current-bearing wire has a current going upward and it's on the left side of the loop, then again, I'm going to turn around so that my hands do the same thing as you would if you were doing this in front of yourself. So there's a current-bearing wire to the left. The current is going upward. Here's our loop to the right of it. So if I wrap my fingers around my imaginary current-bearing wire, to the right of the loop, my fingers are going into the page. Again, the magnetic field is a circle going around my now imaginary wire, and to the right of the wire it's going into the page. Behind the wire would be left. To the left of the wire would be coming back out of the page. But here to the right of the wire, it's into the page. All right, so we have a magnetic flux that is increasing and directed into the page. Next step, step 2, magnetic field due to the induced current points in the opposite direction to the original field as the flux is increasing. So our flux is increasing, so the magnetic field due to the induced current points in the opposite direction. We already figured out the magnetic field points in, so the magnetic field from the induced current will point outward. So we have our answer there. If you don't want to have to stomach all these words, you want to make sense, you can think again. There is an increasing flux going into the loop from that increasing current. And to oppose that change, if there's more flux going into the loop, to oppose that change, you need a flux going out of the loop, so opposite direction. So magnetic field to induced current is out of the loop. Last step, use the first right-hand rule to determine the direction of the current. So I'm going to turn around again. There's our loop. Our flux is coming out of the loop, so I grab from below so that my fingers come out through the loop, and my thumb is going from 6 o'clock back to 3 o'clock. That is counterclockwise. I could grab from the top, but I just want to have my fingers coming out through the loop. So if they're coming out through the loop, then my thumb is pointing from noon back to 9 o'clock. So again, counterclockwise. Doesn't matter where you grab it. If your fingers are coming out, your thumb points in a counterclockwise direction. All right, so we finished that one. That should be a good number of examples to work through. Practice it. If you have questions, email me or let me know in some other way. Hopefully things are starting to get a bit more comfortable. All right, see you soon.